in both theorem 4.2.A and 4.2.B, we need the Lipschitz condition. So sometimes Lipschitz condition is not so easy to check, but we have an easy way to check whether a function satisfies the Lipschitz condition. So if the function is continuous, first partial derivative with respect to yi or I from y. Okay? You have to note that the function actually has n plus 1 variables, right? X by 1 variable. But here I just require that this function is continuous first partial derivative with respect to y variables. Okay? In the closed rectangle in the previous theorem for OI. If this is true, then then F satisfy the Lipschitz Okay. So this is a very simple checking conditions for the function f to be to have the Lipschitz condition. So we just take the partial derivatives with respect to y1, y2, and yn. Just first partial derivatives, and see if all these partial derivatives are continuous. Okay? If they are continuous, then of course it satisfies the Lipschitz condition. Okay? Okay, actually I have a lot of to say about the theory, especially for linear systems. Okay, so let me, but actually I don't have much time left. So I just mentioned some of them. Okay, so now we will consider special kind of system of first order ODEs. So if 4.2.1 can be written as y1 from a11x y1 plus a1n yn plus plus g1x y2 from to a21x y1 plus a2nx yn plus g2x yn from equal to an1x y1 plus an2x plus g&x. Did I use this question number? Yeah? Not yet, right? I did? Oh, so, 6. Oh, 7. Oh, okay. Thank you. Okay, 7. Thank you. Alright, so it can be written as then 4.2.1 is 7 is called a system of first order linear ODEs or a linear system. So that makes that the function, the f function, is a linear function of y1 up to yn. Okay? The coefficient in general is a function of x, a function of x here. So we have a coefficient here, and we have a non-homogeneous term. They are all functions of x. But the point is that the f functions, f1, f2, f3, up to fn, are linear in y1, y2, up to yn. So they are called linear systems. So they are special types of system of first order ODEs. Okay, so if we look at all these systems, okay, so since, alright, so we see that now we check the partial derivatives of fi's with respect to yj's. We find that there is aij x. That's the, for example, this is f1, right? F1. So with respect to y1, we get this part. Okay, so it's a11. So in general, the partial derivative is here. Any question about this result? Okay, so if aijx and gix are continuous, okay, so if the partial derivative aijx and gix are continuous, functions, a closed interval okay. So if aijx and gix are continuous function on a closed interval, then in a linear system, together with an initial condition, specified at x equals 0. I think it's better. Going to that, okay. So with an initial conditions specified at x equal to x0. Alright, so such a linear system, together with an initial conditions, i.e. I will be we can have the conclusion that from theorem 4.2.8 and also the remark here, you know that the partial derivatives with respect to y continuous functions and the g1x, they are continuous functions. Then the corresponding IVD, initial value problem, has a unique solution on open interval. So this is going to be. So you can see that, so it's quite easy to check the conditions in theorem 4.2.8 if you are facing with a linear system, because you need only to check the coefficient functions and the non-homogeneous functions. what are these results? Battery. I don't know if the battery. I have to replace the new one. Okay, now, and solutions. One, and two, and n of before that, I have to say if g1x, g2x, gnx is 0, then the linear system in 4.2.7. So if G1, G2 up to Gn are all zeros, then the linear system is called homogeneous. Okay? Homogeneous. And of course, for a homogeneous system, you always have trivial solution. It means that every function is zero functions. So this is called trivial solutions. So now we say n solutions. Y1, Y2, Y2, and of the homogeneous linear system in 4.2.7. is called linearly independent on an open interval and 0 if C1 y1 plus c2 y2 plus cn yn is equal to the O0, identical to O0 function is 0, 0, I0. So if I can find C1, C2, Cn are constant, so that this linear combination becomes to the all zero functions. Implies that C1 is C2. Okay. So if you can show that the only possible constant such that this is true is that C1, C2 of Cn are all zeros. If this is true, then these n solutions are called linearly independent. Remember, each solution is a vector. And it's a vector. Because in here, a vector has n components, one for y1, y2, up to yn. So each solution is n dimensional. It's n dimensional. And we have n such solutions. A basis our fundamental system of homogeneous linear systems. Among of order n may be that linear system of n among functions y1, y2, yn is a set of n linearly independent solutions of the homogeneous linear system. And such a basis gives a general solution. Okay. And we can we write this linear combination by matrix. How can we do so? Well, we can put all solutions. So we have n column vectors. So this is the first column vector we put in the first column, second column, up to the nth column. Okay? And I put C1, C2. Okay. All right, and this comes to the matrix and the constants. And this is n times n. So this one is an n times n matrix. Okay. So this is an n times n matrix. Which is called a fundamental matrix. So now you have a fundamental matrix here. So a general solution can be written as the fundamental matrix times a coefficient, a constant vector. So you have C1, C2, and Cn. So Cn and Cn are an arbitrary vector in n-dimensional space. So it's n vector, n-dimensional vector, the arbitrary n-dimensional vector. Okay. So we can express a general solution by using the matrix notation. It's very, very concise. Okay. But I hope you will be familiar with the matrix notation. Okay. This is a common trick in linear algebra to write a linear combination of vectors into matrix multiplication. This is a common practice in linear algebra, and I hope you get used to it. Any questions? Now, we define the Wronskian of n vector functions. H as the determinant Wronskian of H defined to be so you can, they are column vectors, so they form a matrix, and we take the determinant. So when you write down, this comes to 1, 1. Okay. So you write the column vector explicitly. So the first column vector consists of n components here. Right? The second vector also consists of n components here up to h. Okay. So this is a Wronskian. Okay. It's a Wronskian for n vector functions. Okay, so theorem 4.2.c. Okay. You will have the same question as before. If you are given n solutions, okay, you are given n solutions for the homogeneous linear systems. Okay, you have to check whether they are linearly independent, because if they are linearly independent, they form a basis. So we can use these n solutions to form a general solutions of the system of homogeneous linear system. Okay, so so here is the result. So let the coefficients Aij that's in 4.2.7 be continuous on an open interval minus 0. Then n vector solutions, then n solutions by 1, 2, up to n, homogeneous linear system. Are linearly independent. Okay. If and only if they are Wronskian. W, linear dependent. Okay. As usual, we check linear dependency. The Wronskian is 0 at some point. X is 0 in the open interval. Okay, so only one point is enough to check the dependency or not. Okay? Furthermore, the Wronskian is 0 at some point x0 in interval, then the Wronskian is identically to 0 minus 0. Okay? Hence, if the Wronskian is non-zero. Okay. At some x1 in the open interval, then y1, y2 up to yn are linearly dependent. Okay, so to apply this theorem, we have to make sure at first that y1, y2, yn are solutions of a homogeneous linear system. Okay, this is the first thing you have to know. Otherwise, the statement here is invalid. Okay, it's invalid. Please understand that the Wronskian, the definition of Wronskian for linear system are a little bit different from the previous one, because in this Wronskian, no repeats are involved. Okay. We just put the vector functions here, okay, to form a matrix and to compute its determinants. Only. Okay. So you have to know that. Oh yeah, this is okay. But actually. This section is very lengthy because I have a lot of to talk with, and so in my schedule I have to finish section 4.3, but you know I haven't finished 4.2 yet. Okay, so So the next quiz, next Monday, I think I will cover only chapter 3. Yeah. No chapter 4. Okay. So, but make sure you take some time to read 4.0 about matrices. Okay. Matrices. And I will talk about the eigenvalue and the eigenvectors of matrix very soon. I'm not sure. Did you learn eigenvalue and eigenvector in your algebra course yet? Yeah, if you took the course last semester, no problem with that. But if you are taking the course this semester, I should worry about that. Yeah. So please make sure to take your time to read 4.0 in your weekend. Okay. All right. So I'll see you next week.